In this video, we will talk about the equation of continuity for fluids. We shall restrict our discussions to the flow of an ideal fluid. The characteristics of an ideal fluid will be given in a minute. We will then define the mass rate of flow, which has an SI unit of kg per second, and volume rate of flow with a unit of cubic meter per second. These two quantities are essential and central in defining the equation of continuity. Next, we shall solve a few problems based on these concepts. Let us first define the characteristics and assumptions of an ideal fluid. An ideal fluid has a steady or a laminar flow, which means the velocity of the moving fluid at any fixed point does not change with time. The second assumption is an ideal fluid is incompressible. That is, its density has a constant value. An important concept that gives us the equation of continuity is the conservation of mass in a fluid flow. To understand this, let us look at the following setup. So you have a flow of fluid from region 1 to region 2. At region 1, the liquid or the fluid is moving with speed v1, and in region 2, it is moving with speed v2. Let's look at this cross-sectional area in region 1. Let's call this cross-sectional area A1, and the cross-sectional area in region 2, A2. Conservation of mass applied to the following system says, in t seconds, there will be certain amount of fluid that is passing through this cross-sectional area into this part of the tube. And at the same time, there will be equal amount of fluid that will be going out of this volume through cross-sectional area A2. Let's assume the mass of fluid that is passing through area A1 into this part of the tube in t seconds is m1. And this m1 equals the density of the fluid times the volume of the fluid that is passing through the region A1 in t seconds. Let's call it capital V1. How do we compute capital V1? Let's assume this is region 1 right here. So the cross-sectional area here is A1. The fluid is moving like that with velocity or speed V1. That means in time t seconds, it would have moved a distance of V1t. So the total volume of fluid that is passing through this region in t seconds is therefore A1 V1t. Note that this little v1 is the speed of the fluid and this capital V1 is the volume of that fluid. So the mass of the fluid that's passing through this region 1 in t seconds is therefore density times A1 times speed in region 1 times time. Likewise, the mass of fluid that is passing through region 2 in the same amount of time t seconds is m2 equals density, the cross-sectional area A2, the speed v2 times the time interval t seconds. Since m1 and m2 are the same, then m1 over t must be the same as m2 over t. From the first equation, m1 over t is quite simply the density times cross-sectional area A1 times speed v1, and m2 over t from the second equation is density times cross-sectional area A2 times speed v2. So what this equation is saying, the mass flow rate is constant for this fluid flow. The unit for mass flow rate is kilograms per second. So the unit of this term and that term is kg per second. Now note that both of these terms have density in them, so they cancel out, and you're going to get A1 V1 equals A2 V2. This is the equation of continuity for the fluid flow. What this equation is saying, the volume flow rate is constant throughout the flow. The unit for volume flow rate is cubic meter per second. So the SI unit for this term and that term is cubic meter per second. It measures the volume of fluid that flows every second across a given cross-sectional area. Let's do problem 1 on equation of continuity. Water is flowing in a circular pipe of a varying cross-sectional area. At point 1, the radius is 0.2 meter. Determine the magnitude of the water speed at this point if the volume flow rate is 0.65 cubic meter per second. At point 2 in the pipe, the water speed is 4 meter per second. What is the radius of the pipe at that point? So let's do part A first. We are given the flow rate. So the flow rate is 0.65. Flow rate, the volume flow rate that is defined as the product of cross-sectional area. And if we are applying this to point 1, so cross-sectional area at point 1 times the speed of the fluid at point 1. Now we do know the radius of the pipe at point 1 is 0.2. So if it is a circular cross-sectional area, then the cross-sectional area is given by pi square of the radius there. So that is R1, that distance right there. That's the radius. So that means A1 is pi 0.2 squared. V1 we don't know. That is what we want to determine. And we can solve for V1 here, and it will turn out to be 5.2 meter per second. Now part B. At point 2, the water speed is 4. So what is the radius there? So at point 2, the flow rate must still be 0.65 cubic meter per second. So at point 2, we do know the speed. So the speed is 4. But we don't know the area because we don't know the radius. The area is given by pi radius at point 2 squared. And we can solve for R2. And when you do that, you will get R2 to be 0.23 meters, or 23 centimeters. And that solves the problem. Problem 2. A hose with a radius 1 cm is connected to a water sprinkler which has 20 holes, each with a radius of 0.05 cm. If the water speed in the hose is 0.8 meter per second, find the speed with which it leaves the sprinkler hose. Let's use the hose data to calculate the flow rate, the volume flow rate. Since the radius is 1 cm, the cross-sectional area is pi 0.01. I'm converting the cm to meter squared. So that is the area. The speed is 0.8, so that's going to be 0.8 meter per second, which will give you 2.51 times 10 to the power minus 4 cubic meter per second. So that is the volume flow rate of the system. Now let's look at the sprinkler. Let's calculate the product AV for the sprinkler. Now, we don't know the speed with which the water leaves the sprinkler hose. That is what we want to determine. But we can figure out the area. Now, each hole is 0.05 cm. So each area is pi 0.05 cm converted into meter. You have to divide that by 100, square that. Now, don't forget there are 20 holes, so the total area can be obtained by multiplying this number with 20. And don't forget the V from here. Equation of continuity says these two numbers must be the same. And you see we can solve for V, which will give you 16 meter per second. So that is the speed with which the water leaves the sprinkler hose, and that solves the problem. Problem 3. Stream of water emerges from a tap and travels vertically downward as shown. The two cross-sectional areas are A1 equals 1.5 cm squared and A2 is 0.5 cm squared. The two levels are 5 centimeters apart. Find the volume flow rate and mass flow rate from the tap. Now we note that the change in the horizontal cross-sectional area is characteristic of any laminar falling stream because the gravitational force increases the speed of the stream. So to first determine the volume flow rate, you need to know A1, V1 or A2 times V2. Now we know A1, we know A2, but we don't know the speeds. But note, this is a problem on motion and gravity. So we can use one of the kinematics equation. And the equation that we want to use here is the following. So let's assume that the speed of the stream there at point 1 is the initial speed, and the speed v2 at point 2 is the final speed. Now the acceleration is the gravitational acceleration, and the falling distance is 5 centimeters, which we can label first as y. So the equation of kinematics that we want to use here is v squared minus u squared equals 2 times the acceleration times the falling distance y. Since the final speed v is v2, so that is v2 squared there, initial speed is u, so u squared is quite simply v1 squared equals 2 times acceleration is 9.81, and let's for now take the falling distance to be y, the value of which we know to be 5 centimeters. However, from the equation of continuity, we can solve, say, for v2. So v2 is given by a1 over a2 times v1. And we can substitute v2 into here, and we will get a1 over a2 squared v1 squared minus v1 squared equals 2 times gravity times y, and y is 0.05 meter. We know a1 and we know a2. So a1 is 1.5, so it's 1.5 centimeters squared. A2 is 0.5, so 0.5 centimeters squared. Note that we don't have to convert centimeters squared to meters squared because it involves ratio. The conversion factor will just get cancelled. Now v1 squared, which we don't know, minus v1 squared equals 2 times 9.81 times 0.05. And you can solve for v1 and it's going to give you 0.35 meter per second. Now using this, we can calculate the volume flow rate. The volume flow rate, let's call it F sub v, equals A1 V1. A1 is 1.5 cm squared. Now here you need to convert cm squared to meters squared by multiplying 10 to the power minus 4. And V1 is 0.35, which will give you the volume flow rate as 5.25 times 10 to the power minus 5 cubic meter per second. Now we can find the mass flow rate. The mass flow rate, let's denote it with F sub m, is given by the density times cross-sectional area times velocity. Now this AV is quite simply the volume flow rate, which we have already found. The density of water is 1000 kg per cubic meter, and FV is 5.25 times 10 to the power minus 5, which will give you 0.0525 kg per second. And that solves the problem. Thanks for watching.